We're going to talk today about the modeling for the pulse oximeter. And while our EK210 kits have a pulse oximeter module that's fully integrated, they also have all the components needed to test individual functions of a pulse oximeter. And these include the OPT101 amplified photodetector, which has a circuit schematic as shown and has the pinouts that are shown. Note that there's a notch in that chip, and pin 1 is directly to the left of the notch when looking down on the top of the sensor. Note also that these pin locations on the schematic, these are pin locations on the schematic, so the V plus, the 5 volts, would go to pin 1 when you hook this up. Note also that the photo detection is shown in this glass box analysis of the circuit as light, wavelength of light coming in and hitting the photodiode. And the photodiode then creates a current. This thing inside here is what's called a transimpedance amplifier, which turns current into voltage. And the voltage is the amount of voltage is determined, the amount of voltage for a given current is determined by this resistor, this 1 mega ohm resistor, which says that you have 1,000,000 times more volts than you have amps coming in. So this is the transimpedance amplifier, and this thing is part of your kit. You also have red and infrared LEDs in your kit. And it's safe practice for any LED to always include a series resistor of 330 ohms to prevent the current from blowing up the diode. And the final thing you have, not really as part of your kit, but as part of your person, is you have a finger. And so you can, with those 2 LEDs and that sensor, you can create a system to test your pulse oximeter. I think that will be part of an exercise that we will do in class and in our assignments. What we want to do is think about what are some math models that are relevant for the pulse oximeter. And I want to go through about 5 examples of models that could be relevant for the pulse oximeter that you can use in assignment 5. First of all, there's power. Your system, your whole design project in which you will use some or all of the components in your kit will consume some electrical power. How much electrical power will be consumed in operating your pulse oximeter? You could model the voltage and current usage by each major electronic component in the system, and then you could evaluate the passive resistance of components. You could evaluate the total power consumption in watts, and then specify the battery capacity required to achieve 8 hours of continuous use, if that was your objective, or 20 hours of continuous use if that was your objective. So modeling power is always a good way to get a hold on some of the design parameters that you'll definitely need to study before you finish this design. Another math model you might use is infrared and visible light transmission, scattering, and absorption. As you've probably already discussed in your class, the way that blood oximetry works is to use differential absorption and scattering of blood that is oxygenated and blood that is not oxygenated. And as your heart pumps that blood into your finger, there's a differential signal depending on the wavelength of the light that you use to interrogate. So explain how light returns to the detector in the same package as the light emitter. If light travels in a straight line, how is it turning around to come back to the emitter? measured the return signals from the red and IR LEDs through your own figure, either using the pulse oximetry sensor module you have, or better yet, use the IR LEDs and the Opt 101P photosensor that are part of your kit. Measure at a number of locations. Measure your earlobe, your wrist, your finger, your thumb. What's the difference? A third model you might try to figure out is the sensor resolution and repeatability. Model the resolution of your measurement. Determine the smallest resolvable change in pulse rate and blood oxygenation that the sensor can provide. It'll be hard to change your own blood oxygenation. It'll probably stay between 100% and 97%, but it's really easy to change your pulse rate. So use an independent measure as a standard for a comparison. Say you could time your physically measured pulse rate at your wrist, for example, or you could use a calibrated pulse oximeter if you happen to have one. Measure the repeatability of your sensor in comparison to this standard. If you're at rest, what's the variability of the sensor reading? How can you reduce that variability to achieve your design goal? Develop a model that shows how the repeatability can be improved through some kind of signal processing, typically averaging. Another thing you could do to model would be to model the signal and noise and how you might improve it in your system. Model the relative impact on signal level of tissue or sensor motion and the pulsatile blood flow. You want to measure the latter and suppress the former. Model how one could reduce the signal due to tissue motion or sensor noise to a level that is smaller than the signal coming from the pulsatile blood flow. That's called the signal to noise ratio. You want that always to be larger than 1. Verify that your model with experimental data and measure the nominal signal to noise ratio of your sensor. And the final model that we'll talk about is portability and durability. You could model how your system will achieve the compact form factor that you require. Develop a CAD model of the package that will contain your Arduino Uno, your power source, your display, and your sensor. This model should be fully dimensioned and should include details of assembly, including all parts, all fasteners, all holes, fully dimensioned, and all interface elements, connectors, and ports. An important detail is how you plan to mount and protect the sensor so that its window is accessible to the finger, yet its circuitry is protected from damage or wear. So we've modeled in very much detail the IR thermometer. These models for the pulse oximeter, I'm just providing you with suggestions. Your job will be to come up with a good detailed model for the pulse oximeter that's comparable to the models that we've presented for the IR thermometer. Good luck.